So our next speaker is going to be Professor Shankar Narayanan. He is at Indian Institute of Science Education and Research, what's called ISER, in Trivandrum, and he is a Ramanujan Fellow of Department of Science and Technology. So his broad research interests are cosmology, black holes, and classical and quantum gravity. And he will be telling us about entanglement entropy in all dimensions.
Okay, so I'd like to thank TRG and Shyam for inviting me and presenting my work. And I know that it's the last talk. I generally expect only the organizers and the speaker to be there, but actually I see more number today. Anyway, so so what I'm going to talk about is something to do with black hole entropy. I didn't put the title here because people have been talking about black hole entropy. So it's something slightly different than what most of the other speakers have been talking. Just fine. There are several approaches to black hole entropy, as you might have heard in the last few days. Now, one of the approaches which stands out for its simplicity and elegance is quantum entanglement. So what I'm going to talk about today is a work which is ongoing work with Samuel Brownstein from University of York, and Saurya Das, who gave a talk and who is supposed to be here. He's there. And then also some work with Saurav Sur, who is currently in University of Delhi. Now, there has been a work which is going on for the last 25 years, starting from Bombelli et al. From 1986, about using entanglement to understand black hole entropy. That is, entanglement as a source for black hole entropy. Now, that has a long history, but what has been people have been not able to calculate is going into higher dimensions, or in instance 5-dimensional black holes. If you want to calculate what should be the entropy and can entanglement actually provide it, is something which is an ongoing discussion in the literature, but people are not able to actually solve it. In other approaches you can do it, but entanglement actually couldn't do it because of some numerical weakness, or basically our lack of understanding. So what we have been able to show is that one can actually show it in all dimensions, going up to 10 if you want to do it. But so that is basically what the topic is going to be about. So I'll give a brief outline of black hole thermodynamics and puzzles, and then I'll go into the details of the entanglement entropy, and I'll just spend a few minutes to explain why we think entanglement entropy should be relevant for black hole entropy, and then I'll go into the discussion of the black hole entanglement entropy, the setup, and then assumptions what we make in calculating them, and I'll first focus on the 4 dimensions and what are the things which we actually understand in 4 dimensions, and what are the subleading corrections one can actually look for in the 4 dimensions for Bekenstein-Hawking entropy, and go into the higher dimensions and then define a new, it's an old one, it's called Rene entropy. I'll just discuss that in detail and then go into the results of it. Fine. Now, what we know is, classically, if you assume that gravity and matter fields are all classical, we know that any particle which actually goes, because of the gravity attracts, then it just goes inside, so we don't have any information about it. So any particle can go into it, so entropy becomes actually infinite, and the temperature actually becomes 0. Now, what we can do is, the simplest is to assume still the gravity is classical, but the matter fields which are actually propagating are all quantum. Then what happens is that the interesting thing is the entropy actually, the temperature no more becomes actually 0, it's actually finite, but it's a very small value. And it is actually proportional to h cross divided by kb, so it actually becomes very, very small. Now, but the entropy, so black hole will not be infinite now, but it will be a finite value, but it will be a large finite value, and it will be proportional to the area of the horizon. You can see that there is actually LP squared, which is a small number, hence because it's actually a small large. So there are several interesting features about it, so I'll just point out only 2 things. So one is this non-extensivity of the entropy. That is, if I would have considered a box of gas and ask a question, what is the entropy of it? How does it scale with how does it scale? We know that it actually scales with volume. Now, in the case of black hole entropy, it doesn't scale with volume; it scales with the area of the surface. Okay. Now, the other thing which is actually quite more interesting, relevant in the case of with respect to understanding how does the entropy of the universe itself is. Now, this relation I have rephrased it in a different way, rephrased it with respect to the mass of the sun, ratio between the mass of this black hole with respect to mass of sun. Now, let us assume that we are going to look for some hundreds of thousands of solar mass black holes, something of that order. then this black hole entropy will almost be actually equal to the entropy of the universe, which is in the free for radiation, for instance. So one solar mass that is of the order of 10 power 5, if you want to consider, then it actually is almost equal to the entropy of the whole universe coming from the radiation and the free particles. Okay. Now, since we know that centers of each galaxy is of the order of 10 power 5 solar masses to 10 power 8 solar masses, so if you want to know what should be the entropy of the universe, so it's actually an interesting problem to actually understand the entropy itself for the black hole. So in the sense, it actually, for numbers to understand what should be the entropy, if you assume that the entropy of the universe is actually constant all through the universe, then it's actually interesting to know what should be where does it come from, this large entropy. Okay, so there is another interesting relation which is related to several talks which we heard the last few days. One is, there is an interesting dimensional analysis one can do with respect to the gravity action and the semi-classical entropy which we actually derive. Now let us consider a 4D Einstein-Hilbert action, which is root minus gr, and I have put g in the Planck units, it becomes almost, it's actually LP squared. Now, if you just do a simple dimension analysis, the dimension becomes L squared by LP squared. It is dimensionless, but I just want to rephrase it in a way, looks at how the dimensional form of the gravity action looks like and the semi-classical entropy looks like. Now, the 4D gravity action looks like, which is some L squared divided by LP squared. The black hole entropy also looks the same. Now, what is more interesting is when you generalize it to higher dimensions and with all forms. That is, I've just included R squared here. I can include any form of r to the power of n or anything I want. Even the Ricci's tensor, Riemann tensor, I can keep on adding it. Then I write down the dimensional form of the gravity action. It looks like this. Now, if you extract it from the Noether charge, which is actually got from the gravity action, it also has the same dimensional form. Okay. So I just wanted to say this because what I'm going to talk about in the next transparency may be relevant. Okay, so what it means is that the dimensional form of the gravity action and the semi-classical black hole entropy, Noether charge is also, it's actually classical, but I'm just saying it as semi-classical, both have the same dimensional form. The question is, okay, so let us take that we have a model for black hole and entropy. So let us take that it gives you the Bekenstein-Hawking entropy and also these corrections. Now the question is whether it is sufficient enough to actually know that, or whether the quantum gravity model for quantum gravity should give what extra changes it actually gives to the Bekenstein-Hawking entropy or to the Noether charge. So that is what I'm asking is, so let us take this is the correct, this is what is the semi-classical correction. The quantum correction should give you some subleading corrections, subleading terms, and we are interested in how these subleading terms actually arise and what are the properties of them. Okay, so in order to illustrate this, what I've given is here is an expression for an ideal gas. Okay, now this is the classical expression for the ideal gas. It is proportional to the volume, and then there is a factor which is V, a log of volume times T to the power of 3 by 2. Now we can derive the same expression in the quantum picture, assuming that these are all ideal particles, non-interacting, and just considering some quantum states for it, and you can obtain this entropy for it, and it's called the Sackur-Tetrode equation. Okay. Now, there's a couple of things which is important. Now, this is all the subleading terms which you actually obtain it from the quantum correction, just by assuming that these are ideal gas particles are all quantum, and you are considering quantum states. Now, in the classically, I could have considered a hydrogen gas or a helium gas or any other gas. It would have given me the same entropy. Now, in the case of the Sackur-Tetrode equation tells you that it depends on the mass of the particle or the ideal gas which I'm going to consider. So in that sense, the classical expression, maybe I would have considered any gas, any ideal gas would have given you the same entropy, but if I have considered, in the quantum gives you something completely slightly different, in the sense it tells you what kind of particles we're actually looking at. It will be different for different particles. And the other, yes please. Huh? No, but it's a log, so I can always put it as minus also, right? Yeah, logarithm of 0, yes. Yeah, I understand. This one, it actually diverges. It's a... So what happens when x bar goes to 0? You get plus line. What it basically tells you, that is actually a full constant. That is the only thing which it tells you. The first line is a classical expression. So the second should go to the first when x bar goes It just gives you a constant. It tells you that there is a plus constant in the classical exponential. It's like what happens in the black hole entropy, that entropy is actually infinite. It just tells you that there is a constant. It doesn't tell you what is there extra. That's what I'm saying. It cannot be. It's like a phase space. When I say it, I always put it to be h cross. I put the classical phase space to be discretized. I cannot have a, otherwise I'll anyway get an infinity. That's what happens anyway, right? There is no unit of phase volume in the classical. Anyway, when we do a classical phase space analysis, when we calculate the partition function, for instance, you always say that I have a 1 by h cross somewhere always put in. No, that is a classical expression. That's what I'm saying. I can just do it. Yes. Yeah. Okay. Okay. So yeah. So the interesting thing is the corrections which we get here will not have. Cannot, only by computing we'll know it, that what kind of corrections it is. We won't be able to know just by classical arguments or by just by looking at the classical equations. We will not be able to understand what are these corrections look like. Okay, so that is the number one. Now, so we have to also look for the standard view of the statistical origin, in the sense what are the microstates for it. And the other thing which is sort of interesting is, generally in the literature people assume that people also derive corrections to the Bekenstein-Hawking entropy. They always assume that the corrections and the Bekenstein-Hawking entropy always arise from the same degrees of freedom, or in the case of ideal gas, it will be the same, in the sense all these corrections arise from the same degrees of freedom. That's what, in the sense of ideal gas, the particles, ideal particles are the ones which gives you this as well as this, but it need not be the same. That is, I'm just going to mention that in the next transparency. Okay, fine. So there are several approaches to the black hole entropy. So there are what I've classified it as bottom up and top down. Bottom up actually assumes some fundamental structures and then starts calculating the black hole entropy. Now what I'm going to look at it is entanglement entropy, which is a semi-classical, and that is what I'm going to spend the time on. Okay, fine. So in order to understand what is entanglement, so I'll just take a simple example of a cavity which has a one mode field, which is a single frequency, let us take, and it has only one excitation. So if you want to consider it, this is like an electron interacting with the photon field. So when it interacts with the field, it will actually excite a photon. It releases a photon. Similarly, there is another cavity which I have, which is also the single photon, single mode with a single photon excitation. Now, what we are interested in is looking at a joint state wave function for this. So we can have two ways of doing it. One is the separable states, which is a direct product of phi 1 and xi 1. Let us say phi 1 is a wave function for the cavity 1 and xi is a wave function for the cavity 2. Now these states can be prepared in a local operation and they are uncorrelated. That is, means that this measurement of 1 doesn't provide any information about 2. But what I have called it as quantum correlation is basically the entangled state. After several states, I have just mentioned one of them. Now these cannot be prepared by the local operation, and the cavities can simultaneously exist in more than one state, and they are correlated in the sense if I make a measurement in cavity, the state of 1 determines what is the electron or the field, what is the state of the field in the cavity 2, and this is what I'm. Now, in general, to define what is how these correlated is actually quite complicated. Now, the only way what we can actually do it, if I have a two-body system, in the sense if I have considering like cavity 1 and cavity 2 and they are interacting, for them actually we can actually do an exact measurement, we can actually quantify it, and that is because of the fact that one can do a Schmidt decomposition, and this value W alpha actually gives you the degree of entanglement to it. Now, there is usually, in order to measure what is an entanglement, what people use is basically the von Neumann entropy. I will be discussing actually the Rene entropy, which I will discuss it in the later part of the talk. Now, which is usually given by trace low log rho, where rho is actually the density matrix. It's a partial trace. I'll explain in a simple example in the next transparency. Okay. And the interesting property is if I calculate the trace of the full system, if I just calculate the density because it's a pure state, then the entropy will be 0. But if I do a partial tracing of either one cavity or the cavity 1 or the cavity 2, it will give you the same entropy. So in that sense, it's actually very useful. Fine. So in order to illustrate whatever I'm talking about and it will be useful for the rest of the talk, I'll be considering a coupled harmonic oscillator, two harmonic oscillators. P1 and P2 are the momentas, X1 and X2 are the position, K0 is a spring constant, and K1 is the interaction term. I'm assuming that K1 is positive. Okay, now I'm considering a pure state, so that means that look, I can consider any pure state. The simplest is actually the ground state. So I'm considering the ground state wave function for the total system X1 and X2. Okay, now this state is actually entangled. So if you rewrite it in terms of the pluses and minus, which is basically in terms of what is it? Okay, I'm rewriting it in terms of the frequencies omega plus and omega minus and x plus and x minus. I have written it here in terms of x1 and x2, and this is basically entangled state. If you rewrite in terms of separately x1 and x2, there will be a correlation between x1 and x2. That's what I'm trying to mention. Now the entropy of this total system is 0 because it's in a pure state. Now what we'll do is, let us say that I don't have information about oscillator 1. So that means that I'm going to trace over the oscillator 1, which is a partial tracing. So that means that I'm going to trace over x1, which is integral minus infinity to infinity, and then I'm going to get a result out of it. And this is exactly can be solved. So the interesting quantity which we will be coming back is r squared, which is omega plus by omega minus. That is two normal modes frequencies, omega plus, omega minus is given by here. Fine. Now one can calculate the eigenvalues and eigenfunctions of this, and they are given by this. All exact expressions because it's simple. Now one can calculate the entanglement entropy. So that is given by, again, that is also is an analytical expression which is given by some log, which is again which is dependent on r, which is a ratio of k plus and k minus. Okay, now this is a plot of that for all values of r. Since we know exactly, we can just plot it. Okay, now the interesting thing is, when the system is strongly coupled, that is when r is equal to 0, that is when I have k1 is very, very large compared to k0. So that means r is actually equal to 0. The entanglement entropy actually becomes infinite. Okay, so when it is a strongly correlated system, the entanglement entropy will be large because we have less information about the system. Now, when the system is uncoupled, that is they are not having it, that is when k1 is actually almost equal to 0, then the entropy actually goes to 1. So that means we have actually complete information about the system. So it's actually important to have, so we are always going to consider something which has actually is an interaction term between the between oscillators. Okay, fine. So now I'm going to make a connection between the quantum entanglement, which is what I've discussed about, and what I'll be discussing about is the black hole entropy, and I'll just try to give a pictorial description of how these two are actually related, or where it is actually, entanglement actually comes in. Now, so this cartoon provides a collapsing of a star into a black hole. The vertical line is the time, and the horizontal, this thing is the space, is a radial coordinate. Now, at some time t equal to t naught, the star starts collapsing into a black hole, and then it forms a event horizon, and then it is eventually a singularity. Okay. Now, before the collapse, the entanglement entropy is 0 because we have complete information. In principle, we have all the information about the matter inside, and we actually there is no lack of information. Hence, the entanglement entropy is 0, and there is no black hole, so we are not worried about the black hole entropy. Now, after the collapse, when the horizon forms, then the black hole entropy is non-zero, and it's very large. Yes. Yeah, I have not made any assumption. This is just a generic. There is no calculation still now. So when I'm saying it, I have the complete information of what if I have the fields. If I have any field which is propagating into this, if let us consider there is a star in the center, and I'm an observer outside, and I have all the information about the field which is propagating in this space-time. No, the star entropy I am not worried about. I am just telling you that as an observer I have access to all the information inside the star also. Okay, so after the collapse, the star collapses and then forms a black hole, and then the black hole entropy will be non-zero. Now, as an observer at infinity, there is no information about the degrees of freedom which are inside the horizon. That is mainly because of the fact that there is event horizon which is formed, and hence the entanglement entropy will actually be non-zero. So both these entropies are associated with the horizons. That's where this connection comes in, and these are purely quantum effects. There is no classical analog to it. Okay, fine. So now I'll just look into the setup and then what are the assumptions we are making and actually going into the computations of it. So what we are going to do is we are looking at metric perturbations of the black hole spacetimes and then looking at the linear equations of it, and then this actually corresponds to a text scalar field in these spacetimes. So I'm just going to look at all these perturbations, and that is what I'm going to look at. So I'm going to look at test scalar fields in some sense. Okay, propagating in this d-dimensional, I'm going to look at d plus 2 dimensions. So 2 is basically the space and time, the space and the radial coordinates, and d corresponds to the angular coordinates. D angular coordinates is what I look at. So I'm going to consider spherically symmetric to make life simple. But I can rewrite the spherical symmetry in terms of something called a Lemaître coordinate, because for whatever we are going to do, it actually becomes, this coordinates, although it looks very cumbersome, it actually becomes, for physical as well as mathematical purpose, it becomes easier. Okay, now the Lemaître coordinate covers, this is the Penrose diagram for the Schwarzschild spacetime. So the Lemaître coordinate, unlike the Schwarzschild, covers both region 1 and region 2. So it is not singular at the horizon. Now, the xi, unlike the r, it is always space-like everywhere in this region, and the tau, unlike the t, it's always time-like for all the regions from r is equal to 0 to infinity. Okay, so that is one of the advantages of this, and it is explicitly time-dependent. As you can see, this r is actually depending on xi and tau, so it is actually explicitly time-dependent space-time. And it corresponds to a freely falling observer, and which basically means that at v equal to 0, the particles have 0 velocity, and then you just start putting in, and then they will just flow into this. That's what it is, and they're all in straight lines. Okay, fine. So that is basically the background setup which you're actually going to do, and one can actually calculate the Hamiltonian of this in this background, and that is given by this expression. And d is again the angular coordinates. I'm just mentioning it to you. And a number of dimensions of the coordinates. Since it's a spherical symmetry, we can write it in terms of spherical polar, and phi and pi are the canonical conjugate coordinates, the coordinates and the momentum to it. Okay, now the next step is basically the quantization procedure, which is what we are actually interested in. So unlike the Heisenberg picture, what we are going to do is a Schrodinger representation, because since we are considering time-dependent situations, it becomes actually simpler to do it. And the basis vectors of this and the wave function satisfying the Schrodinger equation is given by this expression. Okay. Now, so as I have to mention it that we are doing a field theory, and we will have ultraviolet divergences, but we can actually observe these divergences in Newton's constant. So this actually, after the talk, if people want to ask questions, that time I can discuss that. Okay. So we are looking at what are the states we are actually going to do, and how we are going to evolve the system. The next step is actually we have to calculate the density matrix and then calculate the entropy for it. So what we are going to do is we are going to integrate from RH, which is basically the horizon, to infinity. We could have done either way, because we know that if I have a pure system, the system is in a pure state, which is what we can actually calculate. Otherwise, for other things, the measurement is actually not good enough. Weinhaumann is not a good way of measuring if the initial state for the state 1 and 2, if it is not pure, then we cannot actually know, we cannot be sure that the Weinhaumann entropy is a good measure. So in that case, we are going to say that the system 1 and 2 will be in a pure state. So we can either calculate from integrate from RH to infinity, or 0 to RH. So for 0 as a singularity. So for that reason, we are going to calculate only from RH to infinity. So when we integrate over this region, we should be able to get the reduced density matrix, and then that should give us what does the entropy looks like. Okay. So till this point, there is no assumptions. Everything is actually true, is exact. So since it's time dependent, what we are going to do is we are going to make some assumptions in what kind of frequencies. That is, this is a time dependent background with the frequency. So I'm going to say that I'm going to evolve. So what assumption we are going to make is that the Hawking particles which are actually emanating from the black hole are negligible. That is, it doesn't change the curvature of the space-time as much as it is. So that is where we are going to make. That basically means that omega squared, which is a time-dependent frequency, is actually very, very small. So then one can actually rewrite this Hamiltonian into a much simpler form. The time dependence just goes away because of the fact that we are actually saying that the modes are actually negligible, it's adiabatic. And this satisfies a time independent Schrodinger functional Schrodinger equation. Fine. Okay, so now I'll start once. So what I've basically shown is I've discussed what is the setup we are going to do and what are the assumptions we are making. And next step is to just apply it to for 4 dimensions, and then I'll go into the higher dimensions and see what are the results we have. Now the calculation cannot be done analytically. You can do it, but then it has the density matrix cannot be obtained, and then we cannot make sense out of the density matrix. So hence we have to go for the computations, and hence we have to discretize this Hamiltonian. So the pictorial representation of the discretized spherical lattice is like this. So we are looking at a region of a box. Let us take this is 0 and this is infinity. I'm considering a spherical box, and this is region 1 and 2, and I'm going to consider this as a horizon, which is R, which is A is the lattice spacing, and R is equal to n times Na. N is basically is a shell from which we are actually integrating over, and capital L basically is the length of the space, which is actually in principle it is R is equal to 0 to infinity, but for numerical purpose we can actually assume n to be such a large number such that we won't have a boundary effect. Fine. And so this is that is the setup, and this is the Hamiltonian. So as you can see, if you discretize it, you have certain terms which are actually there is a interaction between the nearest neighbor interaction is what is happening here. So this is the potential energy term, and the blue terms are basically the interactions, that is between the nearest neighbors. We could have actually considered even next nearest neighbors, but actually it is actually sufficient to only just consider the nearest neighbor interaction. Those things are actually very, very small, they are suppressed. So if you go back to the harmonic oscillator, which is 2 harmonic oscillator, now it will just be these two, it will be just a matrix of 2 by 2 and with an interaction term. Now what we are having is an n by n matrix, now which actually has an interaction term this is a tridiagonal matrix, so it is having interaction at every point. Okay, so hence, coming back to the two harmonic oscillator case, we will have non-zero entropy if you calculate it just because of the fact that we are actually having an interaction close to the nearest neighbors. Okay, so the setup is, now we have discretized it. Now the idea is, so these are all bunch of harmonic oscillators, n of them, which are interacting. One again can actually go back and then do the calculation and obtain the wave functions for it, and the most general wave function is this. And then you can actually, since it's a numerical thing, you can actually plug it into the code and then ask a question, what should be how does the entanglement entropy looks like? But it doesn't give any information because we really cannot make sense of with different excited states or different harmonic oscillators in different states. It doesn't make sense to actually, it doesn't provide any physics insight into what is the problem we are doing. So what we do is, we make the simplest assumption, which is actually the most simplest, is you assume that the wave function of the total system is a summation of a vacuum state and a one particle state. Okay. So either one of the harmonic oscillators in this n by n harmonic oscillator is in one particle, everything else is in a ground state. So in that sense, we are actually saying that it's a superposition of a ground state and a one particle state, and this is still a pure state. And C naught squared plus C1 squared is equal to 1 because of the normalization. Okay. So now one can actually calculate the reduced density matrix. You can calculate it, but then you have to do it numerically, and this is given by this expression. Once you know what is the density matrix, we can again grind to the same expression and calculate what are the wave eigenvalues and eigenfunctions, and then one can calculate the entropy for different L's, that is angle azimuthal numbers, and L's, and then one can calculate the entanglement entropy for it. Okay. Okay. So now after grind through it, these are the results. So what we are considering is a 300 by 300 by 300 lattice, and the range in which we are going to integrate over is from n is equal to 100 to 200. So let me just go back to this earlier transparency. So capital N is the number of lattice points we are actually starting out with, and this small n is the number of lattice points we are actually going to integrate over from the center. That is what we are going to do. Okay. Okay. And so I have considered two cases. One where it's equal in the sense C0 and C1 are actually the same contribution to the wave function, and the other one where C0 is smaller in the sense the contribution from the ground state is actually smaller than from the one particle state. Okay. So this is the plot of the ratio of entropies, that is, it's a ratio of the state which is a mixed state, which is the ground state, superposition of the mixed state, this is the ground state plus the excited state, divided by this, the entropy of the ground state for the system. What we have done is, we have looked at S of GS means when I put C1 equal to 0 and then calculate the entropy for the system, and then S of MS, which is basically either this case or this case, and then take the ratio of this and ask a question, how does it follow? Okay, with respect to area, which is, this is the area in the sense of it is n, which is with respect to n. So as you can see, this picture, that is the plot. Now this plot actually gives you a much better understanding. So here what happens is that this is the same plot. I have just taken one of the values. This is for values, this is for both the plots. This is for C0 equal to C1 as well as C0 not equal to C1. So what it means is that here S of MS divided by S of GS, which is a mixed state, is equal to some 1 times something which is a function of area, which is exponential, which is actually decaying. Now the entropy for the ground state is actually proportional to area, which actually it has been shown earlier. So that basically means that the entropy of the mixed state, or what I'm calling it as the superposition of the ground state and the first excited state, is nothing but some area times some function which is actually a non-function of area. It's not proportional to area. It is actually some power law of area. And beta is actually always greater than 0, and A1, which is a coefficient, the most important, is actually proportional to the constant C1, which is the C1 here. Okay. Now, so what it basically means is that when I put C1 actually equal to 0, which means that there is no one particle state, now this will all be corresponding to this will correspond to a proportional to area. So that is, the one particle state lead to corrections to the Bekenstein-Hawking entropy if you want to look at it. So, and it's also that it is, since this beta is actually greater than 0, which is actually means that the correction is actually negative in area, which means that smaller the area of the black hole, larger will be the contribution from it, and hence that will actually supersede the Bekenstein-Hawking entropy corrections, which is what you see it even from other places. Okay. So for small horizon area, there will be a large deviation from the area law, and the second term actually will dominate over the first term. Okay, for the small area. For the large area, this is actually very small, and it will actually gives you the Bekenstein-Hawking entropy. Now, the interpretation is when we consider smaller and smaller areas, then the high energy modes are actually excited, and field modes are excited, and hence you get actually the contribution from the one particle state is much higher, and hence you get actually deviation from the area. So this is completely different from the other approaches where the degrees of freedom which leads to the Bekenstein-Hawking entropy and to the corrections are actually identical. Here actually we are disentangle them in the entanglement entropy approach, that the ground state actually leads to the Bekenstein-Hawking entropy, while the deviations, that is the deviations to the power law, is not coming from the ground state, but it is actually coming from the excited states. Since it's again because of the fact that this A1 is actually proportional to C1. Okay, so if I keep changing the C1, you can automatically say that this factor is actually different, and the beta also keeps changing actually. Okay, fine. Huh? The logarithmic, we are doing a numerical analysis, so it's the logarithmic corrections we won't be able to see it. It's actually because of the numerical inaccuracies. Okay, if you can do it much better, one can actually do it, but it actually cannot be done in this approach. Fine. We are not saying that it doesn't exist. It's just that what we can only say is that this is the only thing which we can actually show exactly. That's all. Fine. Okay. So what we have basically shown now is that in the case of 4 dimensions, the entanglement entropy gives you something which is proportional to area and some corrections coming from the excited states. one can actually do it for higher states, but then it just gets more and more complicated. So we are in the process, but we are not actually done any of these calculations. Okay. Now the interesting part of this comes in when whether entanglement entropy, what it gives to higher dimensions. That is, if you want to look at what happens in higher dimensions, in 5 dimensions, 6 dimensions black hole spacetimes, can it say something about how the entropy and area are related, whether it is proportional to area or it is something else? So that is something which actually has not been done, mainly because of the fact that, asymptotic values of L actually dominates in the original relation. So I'll just explain this. This is a slightly technical transparency, but I'll just try to make sure that it is actually simple. Okay. Now in the case of 4 dimensions, you can, what is happening is, so let me just go back to the original. So if you see the contribution to the entropy, it comes from all L's, okay? But numerically we cannot compute for all L's. We have to, at some point, have to say that large values of L we cannot actually include. So that means that those higher dimensions, so in the case of large, so we have to have a cutoff in the numerical calculation. Now you can do an exact computation for asymptotic values of L, that is very large values of L, and ask a question, what is the entropy for it? That you can actually do an exact computation. It's if you can do a first order perturbation theory in quantum mechanics, that actually tells that SL is actually proportional to 1 by L to the power of 4. Okay. Now the numerator is 2L plus 1, so it is 1 by L cube. It actually, so it means that larger and larger values actually gives less contribution to the entropy, hence it actually should converge. So it's actually good enough if we can actually say that we can cut off L at 1000 or 2000 or something, and then we'll be very sure about that the very large values of L do not actually contribute to the entropy. So that is one of the reasons why in the 4D spacetimes one can actually obtain the entropy exactly and show that it is actually proportional to area, even with the corrections. Even though the corrections are very small, we can actually show it. Now what happens in higher dimensions is that this is no more 2L plus 1 as in the 1 plus 1 as in the 3 plus 1 dimensions. It is 2L plus d minus 1 times of weighted function WL, which is given by this complicated function. Okay. Now the interesting thing is, in the larger limit, one can again actually do the same calculation. Now this again actually goes as 1 by L to the power of 4, but since there is a factor of L plus d minus 1 factorial, d minus 2 factorial, which is sitting on the top, and that actually cannot, it just not 2L, it actually L to the power of 3 or L to the power of 4 or L to the power of 5, depending on what dimensions we are actually looking at. So hence what happens is that this factor, which goes as 1 by L cube for large values of L in 4 dimensions, it will not be 1 by L to the power of 3, it will actually be 1 by L, or it is actually constant, or it is actually L. It actually goes proportional to L for large values of L. That means it actually keeps on growing with large values of L, hence the computation of calculating the entropy cannot converge. So that is the biggest problem which people had for a long time. So what people have been trying to say is that you cut off at some L and then see whether one can actually have an area law and whether it actually makes sense. Now you cut it at some values of large values of L and then calculate it, and then it never shows an area law. It might show something which is 3 by 2 or 3 or depending on what cutoff it is. So it is actually so that is the biggest problem actually which has been facing for higher dimensions. So what we have done is we asked a question. So is Voigt-Naumann entropy is a unique measure of entanglement, even if I consider the system to be pure, the total system to be pure, or can I look for something else much slightly different? So we were looking at the literature for a long time, and then we found something which is actually called a Rene entropy. The Rene actually introduced it in 1963, but it has been used by information theorists for a long time, mainly because of the fact that it has some nicer properties, and one can actually play around with a parameter called Q. So that is what I'm going to discuss about. Now the Rene entropy is defined like this with a parameter Q. Okay. Now this parameter is an arbitrary parameter, so that is given that you have to put it by hand. Unlike in the case of Voigt-Naumann entropy, there is no parameter. It is actually a single function which is pi log pi. Now in the limit Q going to 1, okay, this expression you can do a L'Hopital rule, and that will give you a minus pi log pi. So in the sense, when I put Q going to 1, it gives you the Voigt-Naumann entropy. And it is non-negative, which is like Voigt-Naumann entropy, it is also non-negative. it vanishes when the uncertainty is small, that is when pi is actually only when all the values of pi is 0 and only one value is non-zero, it actually gives you it vanishes. And it has a maximum value, again like von Neumann entropy, when all n probabilities are equal. Now it is again extensive like the von Neumann entropy, that is if I consider Pij is a product of two probability distributions, Pi is equal to Pi times Pj, then it is von Neumann entropy like Rene entropy like von Neumann entropy is actually sum of these two entropies. Okay, so it has all the features of the von Neumann entropy except that it is an extra due parameter q which is actually hanging on. Now this kind of makes an additional interesting feature for us, mainly because of the fact that so you can actually do the same grinding except that the form of the entropy is now different. Whatever calculations we have done numerically, we can compute the same thing, SL will be the same, the reduced density matrix will be the same, except at the last point we can actually change the form of the measure of the entropy to be slightly different. So that's what we did, and again what we did is to understand what happens at the large L's and to get an insight of why the von Neumann entropy actually diverges at large L. So what we did is we actually did an asymptotic calculation for large L for the Rene entropy even in 4 dimensions. So in the case of 4 dimensions, what happens is that there is a convergent part which is always 1 by L to the power of 3 or 1 by L to the power of 4. Now there is a term which is actually depending on q, which is the unknown parameter which we have to put it by hand. When we put q equal to 1, it tends to the von Neumann entropy again. I just want to mention it. Now what this basically shows is, this tells you that for q greater than half, this is again, this you should just recall that it should be, this is what we have done is in 4 dimensions. So it converges for all q greater than half, but it diverges for all q less than or equal to half. This we checked it again in the numerics, and it actually showed that for q less than or equal to half, it actually diverges. Right. Yeah, we continued analytically, but the question is, we are doing everything numerically, so I don't know how to do the. Right, but what I'm saying is, I'm interested in doing everything for different values of q, then asking a question, for what, no, this is just an exercise to check whether what we are doing is actually makes sense. Okay, so I didn't understand the question, so I'll. Right. So I understand. Now what I'm saying is we just put this expression into our coding, and then asked a question what happens at q equal to half. It again shows that the entropy actually diverges. So analytically I understand that you can actually do this, but numerically I don't know whether how it can be done. That's what I'm saying. I'm sorry. You can continue it. Huh? So will it be imaginary or it will be a real values? Okay. So the next part is okay. No. Okay. So what we did is we did the same analysis for 5 dimensions and 6 dimensions just to understand what happens. Now what we find is, this is for the x-axis is the q parameter and y-axis is actually the entropy. Okay, and the red the dotted points are the numerical values, and the red curve is basically the fit which we have done. Okay. Now what happens is that as we keep decreasing the value of q, the value of the entropy actually goes on increasing, and actually at q equal to 1, all our computations actually fail. This is in 5 dimensions. So this again you should just mention it that the von Neumann entropy is q tending to 1, that is at q equal to 1 you actually get the von Neumann entropy limit. So that is one of the reasons that where people who use the von Neumann entropy couldn't compute we always get an entropy which is actually divergent for large values, always had a divergent entropy at q equal to 1, and hence they couldn't compute for higher dimensions. So this is again the point which I just wanted to mention it. So but for any value of q greater than 1, we can actually compute the entropy which is actually finite, and it actually converges. This again goes back to the fact that, so here it is 1 by L 4Q minus 1 for higher for 4 dimensions. This becomes actually a slightly different value for higher dimensions. For 5 dimensions, it will be different for higher dimensions. But for larger values of Q, for Q equal to 1, it becomes divergent. It becomes convergent in the Rene entropy limit. So similarly, one can actually do it for Q for D equal to 6. That is 6 dimensions. D equal to 4. You can again see that the entropy when we start from Q equal to 10, the same plot. Y-axis is the entropy and Q is the parameter of the Rene parameter. When I keep decreasing the Q, what happens is that the entropy actually shoots when Q is actually 1.5. So again, you cannot actually compute the entropy for Q equal to 1.5, but for any large values of entropy, you can actually compute and you can actually see that it is actually convergent. So then we can actually see that we can actually calculate the entropy. This is the plot of log of entropy versus log of n plus half, which is basically log of entropy versus area, and for different values of Q. And for all values of Q, it basically gives you entropy is proportional to n cube, which is the area for the higher dimensions. In the case of we are looking at D equal to 4, which is 6 dimensions. We are showing that we have shown that for all values of Q, this is Q equal to 1.1 to Q equal to 20. For all values is actually a linear fit, and it actually is proportional to area. So similarly, what we have done is we have actually looked at higher dimensions, so 6 dimensions also. So even in 6 dimensions, we started out by this is not 1.5, it's 1.55. So we actually looked at all the values of from 1.5 to Q equal to 10, and again we have computed the entropy for it. And for all values of Q, the entropy actually comes out to be proportional to n to the power 4. So there is, in the case of the entanglement entropy, it doesn't depend on Q. The prefactor may depend on Q, but actually the values, the index for the n actually depends on pure number, which is actually the number of dimensions. Okay, so in that sense, what we have basically shown is that one can actually use a different definition of entropy, not the Neumann entropy as a definition of the quantifying this thing, and actually compute what should be the entanglement entropy for these systems, and it actually gives you area for all dimensions. Okay, so I'll just stop after discussing a few points. So what we have basically, what I've tried to tell you is that you have to why we need an approach to go beyond the black hole entropy and provide a generic subleading corrections. So what I've shown in the case of 4 dimensions is that the ground state gives you the Becken-Schonking entropy, but then the higher order one excited state, first one particle state actually gives you corrections. And basically you have to identify the degrees of freedom that contribute to the black hole entropy and its correction. These are actually different, at least in this approach. Okay, now the degrees of freedom that contribute to this are different, and the power law corrections are different, and they are actually different from the Noether charge. Again, I just wanted to mention that what the people have obtained from the Noether charge, the Waltz entropy, are actually different than what we are actually obtaining from here. It gives you area proportionality in higher dimensions. We have not looked at the excited state, but actually it should follow through, but we have just not done the numerics for it. Now we have asked a question whether what we have done is for the massless field, whether it works also the area law holds even for the massive fields. We have actually looked at, and the area law actually behaves something like a S naught, which is for m not equal to 0, for m is equal to 0, and gives an exponential suppression for large masses. Now, recently there have been attempts to look at other people have shown that in the case of 5 dimensions, the topology of a spherically symmetric black hole is not just S3, it can also have S2 cross S1. But people are not able to compute the entropy for it. So what we are looking at is to extend it to, using the entanglement entropy, we can actually see whether what kind of entropy it leads to for S2 cross S1 black hole in higher dimensions. So that's what we are actually looking at. I think I'll stop at this.
I just have one question about this degrees of freedom that lead to your A entropy counting. The degrees of freedom that contribute to this SBH come from the degrees of freedom on the black hole horizon and which are inside the horizon, you're saying, right?
Okay, so I didn't show the pictures because of the lack of time. So one can actually look at where, from what region of the space we can actually identify which one contributes maximum, which one contributes little.
Yeah.
Around the horizon, two lattice points from the horizon actually contributes up to 97% of the black hole entropy for the ground state. For excited states, it's not 97%, it's actually very, very small, but the ones which are actually even very large from very away from the horizon also actually contributes to it.
Okay, but yeah, but that looks very strange to me, because you see, the concept of black hole horizon, black hole entropy or things like that, that come from the first law of black hole mechanics to start with, right? So
Right.
for first you have to write down the black hole mechanics, and then you say that, well, you can identify the area with the entropy and things like that. But inside the black hole horizon, we don't have things like first law. So to make statements like there might be degrees of there might be degrees of freedom that contribute to entropy, that is very seems very strange to me.
So okay, so let me just put it in a different way. So what we are looking at, this is all purely classical, right? What you are doing is, it's completely classical. So we don't have any information with anything within the horizon. So what I am saying is, we are here, there is an interaction between the, if you want to look at it, let me just go back to the transparency. Okay, so let us look at these. So okay, no, again I made a mistake. Okay, so here, now here what we are looking at is basically looking at bunch of harmonic oscillators which are actually interacting among themselves. Okay, now since it's an interaction term, any perturbation I do, it will always propagate in all from, it's not just within the horizon or outside the horizon, it actually should propagate everywhere. That is the way I look at it. I am just giving if I give any perturbation, that actually is like on a lattice, it's all connected by chains. I give a shot at one point, it will actually propagate to the other side of the system.
Yeah.
Yes.
The strange thing about this is that for small mass, for small area black holes, your leading corrections becomes sometimes greater than the.
Which is true even for the Beckens for the Noether charge also. Noether charge exactly has the same behavior. It also has a 1 by a to the power of beta, but the beta which I wrote down is completely different than, because that is actually can be determined exactly. That also actually if you look at the Jacobson and Mayer's paper, they actually show that for small black holes it doesn't have it doesn't have an area law. So it is a feature which is seen in all these corrections actually. Yes.
From my understanding, this 5.1 and 5.2 are fluctuations of the metric, right?
5.1 and 5.2.
What are these 5.1 and 5.2? Scalar fields.
Oh, scalar fields, yes.
Okay.
Yeah.
But this is very puzzling, because Minkowski space, if I two scalar fields are coupled, and I integrate over one, I'll get an entropy. Okay.
Yes,
In
this
the ground
is basically what Schrödinger did. This is exactly what Schrödinger did.
I don't know, but so this is not the entropy residing at the horizon in the black hole. This will happen in a flat space. If I take two scalar fields which are coupled like this, you lattice or do
Right.
what you like, and integrate
Yes.
over one, you will get an entropy.
Entropy, yes.
So it's very, I
Right.
don't know.
But so that's exactly what I'm saying. So it can be done. It can have, you can create situations where it can be done. I'm not denying anything what you're saying, but it comes into a physical it attains a physical meaning only in the case of a black hole.
Can I
horizon.
finish my
Yes,
statement?
please. Sorry.
Furthermore, so I am not sure that, following his remark also, that this calculation says anything about the Bekenstein-Hawking entropy. And let me also make a remark. The vacuum, it is notorious that vacuum is highly non-local. That is, to define the vacuum state involves data over all your spatial slice. This is one of the things that people keep, even people like Bob keeps emphasizing. Okay? So the vacuum state for which you are computing it cannot be localized, at least so, to my knowledge. And finally, this is very different from what Luca Bombelli and Raphael did, okay? Raphael Sorkin did, where they were computing the some state and partially tracing over
Exactly,
states which are inside.
that is exactly what we are doing here.
No, they were taking states at the boundary of the horizon, or the vacuums, or the field. Yes.
I don't agree with that. They
It's
actually
already
did, if you look at their paper, they actually did the same thing. They actually considered spherical, they don't consider, they considered a spherically symmetric space-time, and they exactly did the integration from r is equal to 0 to infinity, and then calculate what is the entropy for it.
The state, from my understanding, was coming because of the coupling across the horizon. Let me put it that way.
This is also happening exactly because of the horizon.
Because
That's
this will be there even for a Minkowski space. You will not get 0 for Minkowski. Huh?
that is exactly what I said.
Framework will give entropy in Minkowski space.
No.
I have two questions. First one is that when you put a lattice cutoff, you would expect to get a finite answer. That's true for Bombelli and Meyer and all that. Yeah? But you seem to have one extra divergent sum coming from L. I don't quite understand that.
No. Okay. So this is nothing to do with L. So what happens is that okay. Can I just 1 minute? Sorry. So okay. So what I'm saying here is, if you rewrite the SL values for large values of L, and what is happening is that if you use the measure of as a Voigt-Norman measure, it gives you completely good result for 4 dimensions. Okay, but in higher dimensions we are not able to compute it, mainly because of the fact that if you have to keep computing for all the values of L. For all values of L, if you compute, then eventually you will be able to do it. But numerically we cannot do it because of the fact that those terms still, higher and higher values of L still contribute larger and larger.
No, L is the angular variable on this.
Angular variable, yes.
So if you go to sufficiently high L, you would be going to sub-lattice distances, isn't that right? So wouldn't that suggest that you should cut off L when it becomes smaller than the lattice spacing? I don't know if I'm making this clear. Maybe we can talk later. Maybe we.
Okay. Yeah, and I understand what you're saying. Yeah, we have. Yeah.
No, I was just saying that if you go to large enough L, you will be going below the lattice
But
spacing.
okay, so there is in my expression, none of my all my Hamiltonian, the LA is actually outside my expressions. So I can always say that I'm considering a sufficiently smaller value of A. So I can always say that the A which I actually put in is actually much smaller. I keep on putting in much smaller values of A. So that means I'm going for higher and higher values of L. That's what I do if I'm considering a larger and larger values of An. I always consider much and larger values of L.
No, you have to keep A finite or the whole calculation will diverge anyway. We know that, right?
Right,
Because,
but
yeah.
that A itself is an arbitrary parameter in my this thing, because it doesn't appear anywhere in my equations.
Right. But once you fix the lattice, suppose you take a fixed lattice,
Right.
that suggests that you should cut off L at a suitable value related to that lattice. Maybe we can discuss it later. That's
Sure, okay, yeah, fine.
my second question is that if you have this interpretation, which of course many people have, there's the species problem in the sense that if you consider 2 scalar fields,
Right.
you'll get twice the entropy.
Okay.
So just what is your attitude towards
Okay, so what happens is that so that can be killed in one shot. Actually, there is a recent article by Braut 2 years back, so where he actually mentions this. So you have a ultraviolet problem and you have a species problem. Now, so these two problems also affect the lambda, the cosmological constant problem. So you have a ultraviolet cutoff and you have a n number of species. So what you can say is you ask a question. So and we don't know any of these, which is the correct. So n is the number of species in the universe, which also we don't know. For instance, used as a constraint to constrain n and the ultraviolet parameter. Then what he shows is which I think he has not done a full calculation, but I think he shows that so both these parameters actually go away, and then finally there is only LP which is actually standing. So in the sense you are actually killing both the things by saying that I say that the lambda is a observed quantity, and I want to fix which will be contributing both to the entanglement entropy as to the lambda, and then I can actually circumvent these two problems. Actually, it's actually a very interesting paper. It appeared 2 years back.
Just
Yes.
going back to this question of the relevance of the black hole here. Supposing I did this calculation instead of going to higher dimensions, etc. I do it in 2 plus 1 dimension, 2 dimensions.
You can do it to 2 plus 1. You can do it.
Well, you will get the same thing, identical, except the
yeah.
dimension will
Sure,
be
sure,
changed.
sure.
You will get the same entropy,
You get the entropy. Yes.
right?
Yes.
But we know in 2 plus 1 there is not even a black hole, except you go to cosmological constant.
Right.
So even in a situation when there is no black hole, by this computation, you are getting an entropy for some fictitious black hole.
Yeah.
So it has no relevance to black hole is probably what is more appealing.
No. I don't agree to that. So what I'm saying is, you're saying that, okay, so let us take the case. So let us consider ideal gas, and let us take that in this system I can say that I can define it in a state which is a pure state, and I entangle it with two ideal gas molecules. Now, or n number of molecules in this thing. Now I'm saying that these two this will have entropy. Okay. Now this will also, I can have it, this can also have an entanglement entropy just because it's correlated. Now that will be much smaller than the thermodynamic entropy which you actually calculate. That's what I'm saying. So it's not that it only comes into relevance only for the horizon black hole. That's the reason why the transparency which I mentioned, yeah. So this transparency is basically tells you that I can always create a horizon, which is basically what Srednicki did. Which Srednicki and Bombelli et al. Actually did the same thing. They just put a sphere and then say that we'll integrate over it and then see what happens. Okay, and they get a proportionality area. But the point is that this analogy becomes much more stronger. It makes an effect. It comes into effect only with the horizon, because the horizon for an outside observer is a one-way membrane, in the sense you don't have access to information. That's what it says. Yes, please. Yes. 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 I can put in a mass. I can put in a cosmological constant. There is no issue into this cosmological constant. What I'm saying here.
Even without cosmological constant, you will have it without it, because there is no need for a cosmological constant.
Correct.
Right?
So.
That kind of a metric, you will have a fake kind of a horizon, and you will compute some kind of a entropy,
Right.
which is not occurring in your gravity theory of 2 plus 1. Again, it's only fake.
So that's what again my point is the following. You can all these things you can construct it, but the only place where it actually gives you a sufficient evidence to have it is basically only the horizon. It's not that it is a possibility that one can have it. It's as good as any other approach. That's what I'm saying. There's nothing else.
Can I just no, I will just make one comment. You can, yeah, can one make sense of all this 2 plus 1 and 3 plus 1 by saying that you are going that an accelerated observer sees the Rindler horizon, and that's why you don't need to put the black hole metric there or things like that.
I didn't understand the question well, actually.
Suppose you don't have a black hole horizon, but still you can have a Rindler
observer. Yeah, you can have an accelerating observer which will have a horizon. Yes,
and you can see
you can do that.
Yeah, but then
You can this result will go through that. So so forget even that. What I'm saying is you just take a Minkowski space. You don't consider Rindler metric. You don't have horizon. You just, for fictitious, you say that I'm going to remove certain part of the space, and then say that I don't have access to it. Still you will have an entropy. That's what they're asking. So I understand that will always happen, but the only thing when it actually comes into effect is only when they have a horizon where it actually makes all this things, physical picture comes into picture. That is what effect. That's what I'm saying.
Yeah, I just can I make a brief comment? I think probably the correct point of view is like, you can do all these things in Minkowski space, of course. I mean, you can choose to have a horizon or whatever, and you can choose not to look beyond it, and then of course you end up with an entropy, we know that. But for a black hole, it's gives a natural setting. I mean, there you don't have a choice, right? I mean, if you have a horizon, you cannot look inside. I mean, it's not that you can and you choose not to. So for the black hole, the entropy, comes, it's a natural thing associated with the black hole, which for Minkowski space, it's an exercise, an academic exercise you can or you may not. So for black hole, I think the calculation, of course, goes through as you use the Lemaitre coordinates and stuff like that. But there, the entropy is something real because the horizon is a real